A modern processor runs at billions of cycles per second, yet it can be slowed down if its data is forced to wait in a single-file line to complete basic addition. In a standard ripple carry adder, the final stage cannot output its sum until the carry bit moves sequentially through every preceding block. Stage 2 waits for Stage 1, Stage 3 waits for Stage 2, and so on. When you string 32 or 64 of these adders together to process modern word sizes, that sequential waiting creates a propagation bottleneck. The physical silicon is fast, but the architecture creates a cumulative delay for every bit added. To break this chain, we use a carry LookAhead adder. We are going to use algebra to bypass the sequence and calculate all future carry bits simultaneously. Physical hardware speed limits are ultimately mathematical problems. By calculating dependent variables in parallel, we reduce the total processing time from the sum of every stage to a fixed number of gate delays. This diagram shows the complete logic gate schematic of a standard 1-bit full adder. We start with 3 basic inputs on the left, the 2 data bits A and B, plus the carry-in from the previous stage, labeled C. Look at the logic condition we call carry generate, or G. A carry is guaranteed to be produced at this position if both data inputs A and B are 1. This condition is calculated by a single AND gate. Now consider the carry propagate condition, or P. If either input A or B is 1, any incoming carry bit will propagate through to the next stage. This is handled by the top XOR gate. Notice the pathways for both P and G. They rely entirely on inputs A and B. Because they do not interact with the slow carry-in line at the bottom, both of these signals are valid after just 1 gate delay. With P and G isolated, we can rewrite the math. The final sum is now the propagate signal XORed with the carry-in. And the carry-out happens if the bit generates a carry or if it propagates an existing one. Identifying and isolating variables that do not depend on past data is the crucial first step in moving from sequential to parallel computation. Let's apply this new formula to derive the very first carry bit, C1. It relies only on the generate signal, the propagate signal, and the initial input carry, C0. When we step up to calculate C2, we hit a roadblock. The formula is G1 plus P1 and C1. Written this way, the equation still waits on C1 to be calculated first. But we already know exactly what C1 is. We take the entire formula we just derived for C1 and swap it in for the C1 variable inside the C2 equation. Distribute the variables across the parentheses, and the equation expands. C2 is now calculated using G, P, and the immediate starting carry, C0. It no longer relies on the result of C1. If you take this expanded block for C2 and substitute it into the base equation for C3, the resulting formula grows even further. This logic diagram visualizes that expansion. C1, C2, and C3 are now produced concurrently through independent gate paths. This pattern expands all the way up to C4, generating all carry bits at once. Algebraic substitution directly translates to physical hardware independence, neutralizing the ripple delay by allowing each carry to be calculated in the same amount of time. This block diagram demonstrates the completed 4-bit carry LookAhead architecture. Instead of passing bits down a line, the central generator feeds all 4 adder stages simultaneously, relying on the immediate availability of P, G, and C0. There is a practical side effect to this process. Unrolling the formula to C4 creates complex equations packed with up to 5 interconnected terms. In hardware design, this creates an issue known as fan-in. Processing these equations requires logic gates capable of taking 4 or 5 inputs at the same time, which increases the physical complexity of the circuit. To manage this, engineers don't unroll the math for every bit. For processors wider than 4 bits, they use hierarchical blocks to group sections of bits together, keeping the hardware requirements manageable. Mathematics provides the logic to remove sequential dependency, but physical engineering must still account for the space and gates required to build these complex parallel paths.